Hey you guys, today I'll be showing you how I solved a problem of tanks mixing using C++. You may know how to do this from a differential equations class you may have taken, but today we're going to try to implement that into a C++ program. Basically in this video what we're going to go over is how to create a system of equations modeling the rate in and rate out for each tank, which will then become a 2x2 matrix. We'll then find the eigenvalues of that matrix. We will then plug in those eigenvalues to find a new matrix, which will then be reduced to echelon form in order to find the eigenvectors. After that, we'll find our general solution, and we'll use Cramer's rule to solve a system of linear equations. Once the math is done, we'll take a look at a few more things the program does. This is what the program's going to look like when the user runs it. It's basically just a depiction here of the two tanks. They've both got some amount of salt, they've both got a different volume, or they could be the same. And there's a rate in and a rate out of tank 1. You can see I've set up the program to automatically default to the values at the bottom. This is the start of the code with just 3 functions, mainly to row reduce or enter a custom time. The program starts off by initializing the default values. After that, it's going to ask the user 3 questions, starting with whether or not they'd like to change the volume of the tanks. Then it'll ask if they'd like to change the rate. Then it'll ask if they'd like to change the amount of salt in either tank. So to start calculating this problem, we're going to have to set up 2 equations. One for the amount of salt in tank 1 and one for the amount of salt in tank 2. How we're going to do that is setting up rate in minus rate out. The calculations I'm about to show you are the ones that I've used for the following numbers. They're different from my default values, but this program should be able to run using any value. I'm providing you with this in case you want to try to duplicate the calculations yourself. So here's the math we need to do in the program. We've got to set up the 2 equations. We need our initial values, and then we're going to have to compute the eigenvalues, which you can see below is lambda times the identity matrix minus our original matrix, which is from our system of equations. We set that equal to 0, find the determinant, and then solve for lambda. This is how I set up my system of equations. You can see there the 2 equations on the top, and the coefficients a1, b1, c1, and d1. Finding that determinant is going to result in a second-degree polynomial, which can be solved for lambda using the quadratic formula. And now that we've got those values for lambda, we're going to plug those in times the identity matrix minus our original matrix, and then we're going to put that into reduced row echelon form for both values of lambda. So because of the quadratic formula, we've got 2 values for lambda, the plus square root and minus square root. After plugging in lambda, this is how the matrices have changed. You can see I've turned the components into a 2x2 array, which is then passed into the function row reduce. This is the row reduce function, which can be changed for any array. Let's say you had 3 tanks and you need a 3x3 array. You can easily change it just by changing the amount of columns and rows, and this will work. It basically just checks for a 1 in the lead position of each row, and then it divides out the rest of the row and turns the digit in the row beneath that 1 to a 0. The whole point of plugging in lambda and then row reducing was to find the eigenvectors. The eigenvectors are going to be used to find our general solution. The last thing we need is just c. So by plugging in t equals 0, we can solve the system of linear equations using Cramer's rule. This part is interesting because all you're doing is solving one equation for c2, plugging that into the next for c1. It just so happens that the variables that we're using, our eigenvectors, are made up of their individual components preceding this step. This has been done so that no matter what kind of custom values the user wants to enter, you're still going to be able to calculate a result. So now that the math is done for this problem, we've got our general solution of equations. And what I'm going to do is create 2 arrays, 720 size, and because our flow rate is in minutes, so 720 minutes is 12 hours. So we're going to see if these tanks are mixed after 12 hours. So before displaying a results table, the program is designed to tell you, hey, are they finished mixing or are they not finished mixing? If they are finished mixing, it will tell you the concentration in both tanks. If they aren't finished mixing, it will tell you both concentrations so you can see the difference. So this step is designed to stop the calculation as soon as the tanks are within 0.01 units of each other. I say units because it could be pounds, it could be kilograms, it could be, I don't know, moles. The program then does a little calculation to turn the minutes into hours and minutes, because, I mean, what is 461 minutes, right, in hours? So it'll tell you, oh, this is 7 hours and however many minutes. So this is a function that allows the user to enter a custom time. Let's say they want to figure out if it's finished mixing at 3 hours or where it's at 3 hours, or if you want to specifically zoom into when the moment they become mixed. So here's the program running. It starts off by asking the user if you'd like to change any of the default values. You say no, no, no. Before the resulting table of outputs, it's going to say that they're finished mixing, it's going to give you the concentration, and then it's going to begin the output table. Then you can see the calculation stops once both tanks are within 0.01 pounds of each other, and then it turns those minutes into hours and minutes, so it's easier to read. And this is what it would look like if you decided to enter a custom time. I just wanted to remind you guys that you can change this program up just by changing the original matrix. If you've got more pipes coming in or out of these tanks, you can just add more rate in or rate out variables. If you wanted to create a 3-tank system, you could probably just create a 3x3 array where the third equation is representative of the amount of material in the third tank. Well, thanks for watching my video. I did this all for fun. Hopefully someone will find it helpful.